So good morning, everybody, and welcome to the second webinar we're presenting from IDEC on questioning machine integrity. This morning, we're going to talk about the performance level minefield. And this is just an introduction, and it's part of a complete training that we do on the subject. So just a brief introduction of myself. I've worked in machinery safety for now 25 years, worked alongside people in product development and improving designs. Done risk assessment, allocation of functional safety on machinery in a practical level with engineering experience of remediation. And I'm part of the team from IDEC, the growing team of IDEC safety specialists who understand automation and safety. So in the previous webinar, we had talked about the safety life cycle, going right the way through from risk assessment right the way through to maintenance. And in this webinar, we're now going to talk about the safety performance levels. And with that, we've got all of the PLs and everything to do with the safety, the frequency of exposure and probability of exposure, and all the mathematics that goes in to bring that to the calculation at the end. So this is probably the most misunderstood expression in the safety world. And just excuse me while I mute my speakers so I can't hear something. Okay. And we're going to be talking about EN ISO 13849 Part 1 and a little bit about Part 2 as well, which is the validation of the standard. And we're looking at the safety-related parts of the control system, SRPCS. So safety performance levels, and they cover electrical, electronic, mechanical, and some programmable equipment as people start to use and continue to use programmable PLCs with a safety aspect built into them. So a little bit of history. Let's have a look and see what happened in the past and why we've arrived where we are today. And I have to emphasize this is nothing new, as you'll see in the next few lines. So we've taken a path where we've moved the standard that was EN 954 for safety-related parts of control system, and we've moved it across to EN ISO 13849 Part 1. And we've moved from being a deterministic standard, where very much you made it work, left it alone, to a probabilistic standard, which started to be much more analytical about the reasons why safety functions failed to perform. So 13849 took over from 954 on the 31st of January 2011. So this is nothing new, yet every week I meet people who are still asking me questions about how they should make their calculations. It moved from deterministic to probabilistic, including qualitative aspects as well, to address the systematic failure. And it went all the way into dealing with the project and who's involved in the project and the project team from beginning to end, from risk assessment to validation. And it established qualitative and quantitative aspects that affect the performance of the hardware. And it made a significantly better link between the appropriate risk that existed on the machine and the appropriate architecture in a much more logical manner. So why was change needed? Well, we had previously got what I would call a fit and forget attitude. And there were a series of things that continued to lead towards control-related accidents. We failed to take into account the lifespan and the way people used equipment and the devices that make up their safety functions. The deterministic approach didn't really deal with what was going on in the real world. It was very theoretical and didn't address the utilization at the customer's plant. And so we would take a group of devices, add them together, and we would check that they functioned, but not how they would perform that function over time. We very rarely looked at integrity, and we certainly weren't checking the reliability of those devices given the utilization that we would go on to find out about. So when you look back at the machinery life cycle, we did nothing to establish the effects of incorrect component changes. We didn't deal with competency. We didn't deal with aging of devices or appropriate techniques of management within companies to avoid abuse. We didn't deal with anything to do with alteration of devices in the field. And during the design phase, was very little done to avoid systematic errors and very few qualitative processes to make sure that the safety function would be performed. So from a report a long time ago, and again, the statistics that I used in the previous presentation, at the design stage, when the machine is being built or when the machine is being visualized in the way it was going to be in the plant, 44% of control-related errors were at the design stage. And 32% of them came as a result of system integrity failure. The actual devices were not performing as expected as they should have done, even though it was a perfectly good safety design. So there were characteristics going on that affected that. And then when the devices were in the field, utilization and maintenance, 15% of failures of safety-related controls happened because of things that maintenance engineers were doing or lack of doing. And then changes in after commissioning, modifications, adding on additional devices, adding on additional machines, changing components from one device to the other that functioned the same, but their integrity was different. And therefore, there was a risk and a failure could have occurred as a result. So let's have a look quickly initially at these first 6 steps plus one final one. We need to look at the SF&P. We'll come on to that. We have to understand the performance level that's required for our application. We need to look at the way we're going to design our safety architecture, the risk categories. We have to calculate, now we get onto the maths, the MTTFD, mean time to failure to danger. And we need to also identify a level of diagnostics on the machine to ensure that we pick up errors in sufficient time before the hazardous event occurs or before you've been exposed to that hazard. And we'd have to look at common cause failures. And if we take all of that into account, we can then say that our performance level has reached the performance level required. But finally, and the bit that so many people fail to do, is validation. Did it actually perform as expected? Did it perform as it was identified in the risk assessment? So, what is a performance level? It's a value that defines the ability of a safety system to deliver its safety function in foreseeable conditions. And pretty much it goes from low to high, A being the lowest level and E being the highest level. And we perform a risk assessment, and that risk assessment makes a statement that the performance level required of your safety function shall be A, B, C, D, or E. And the exercise that we have to go through is verify that our design has actually achieved the performance level that was defined in the risk assessment. Now, I have to emphasize, previously I spoke about risk assessments, the generic risk assessments of machine, but now we are specifically talking about the risk assessment in ISO EN 13849, and that specifies how you allocate the safety functions to protect against the hazards that have been defined within the machine. This is about making your control system keep you away from that chopping blade. So now we look at the SF&P, the severity of injury. We have to define whether or not the severity on the machine is minor or serious. S1 for minor, S2 for serious. And when we're doing that, we are not looking at a machine that is guarded. When you perform this risk assessment, you have to review the functions that are going on in the machine, and we are going to use this process to check the adequacy or the design of the safety function that's going to keep us separated from that hazard. So anybody who does a risk assessment on a fully guarded machine and says it's safe because it's guarded has missed the point. We're doing this to ensure that there is appropriate safety functions on board combined with the mechanical guarding as well. And then we have to look at the frequency of exposure. F1 or F2. F1 is seldom, not a very or a short period of time, and the frequency of that exposure is 1/20th of the maximum operating time of the machine, or less than one time in every 15 minutes. And if we go to F2, it's frequent or continuous. I'll give you an example of frequent. Frequent is obviously the guy standing in front of the machine, operating, placing the product in, pressing 2 buttons, taking the product out, very high frequency. But then we also have to take into account the engineer who goes inside the machine, and he doesn't go in more than once an hour, but he does go in and stays within the machine for a long period of time where he changes a component or does some maintenance. So we also take that into account, how long you're inside the machine. And then there is the possibility of avoiding the hazard. So it depends on the occurrence, the speed of the danger, the ability to escape, and training and supervision as well. Training and supervision being the least important of all of the things, because we should ideally design our safety function to prevent exposure to the hazard. But it's inevitable that there is residual risk, and the training and supervision can help you identify that and keep you away from it. So possible under certain circumstances and conditions. So I open it up, there's a high-speed rotating blade, and it's blowing high-speed air at me. I'm probably going to be aware that that blade is rotating, as opposed to scarcely possible, where I open it up, I don't recognize the blade is running, and it's the last thing that I come into contact with. So let's have a look at starting to build the architecture. We do that initially with block diagrams. And the great news is I am not going to do wiring diagrams at all during this. We're just going to talk conceptually. So first of all safety systems have to be built up with an input device, a logic solver, and an output device. And at categories B and 1, we keep it very simple. It's just standard devices at B where we've got reasonable reliability. We understand how they're used. They're well tried and tested principles. But when we go over to category 1, we continue with those well tried and tested principles. But we then start to integrate the use of cabling to go from PVC. Maybe we put in some armored cable to give it protection. Instead of having a limit switch, we put in a safety switch. And each one of those devices offers an increased level of reliability. And so it goes on with the output devices, and we move from a standard relay over to a positively guided relay, and so it goes on. So category B and 1 is simply the step that you go through. The control will be the same, but the devices will offer a significant improvement. So when you look at category 2 architecture, you'll see a similarity because we've got our input device, our logic solver, and we've got our output device. But then we have a whole new entity going on in the side here, which actually is called the test equipment. So we have an input, logic, and output. But then because a single failure could lead to the loss of the safety function, we need to try and identify when that failure occurs and then create an annunciation to say there's something wrong. Now, we don't have a second emergency channel, but what we can do is on a test at a particular interval, we can then say, here's the test, we've detected there's something wrong, there's a big light shining, and it's going to warn the operator that he shouldn't go on because the safety function has detected a fault. It doesn't guarantee that that fault has been stopped on the machine, but it gives him sufficient warning and sufficient time before he gets exposed to the hazard. Now, depending on the risk category that you want to achieve, which we'll talk about later on with its performance level, you can actually use it up to quite a high level. But generally, people use this for machinery where you have a low risk application. You're going to cut your finger, maybe go to first aid, and then come back later. So for more dangerous applications, we would be looking at categories 3 and 4. And the architecture for 3 and 4 pretty much looks the same. We have input, logic, and output, but we have a second channel of input, logic, and output. Where's the mouse gone? Input, logic, and output, which then monitors in parallel the function through the logic solver. And that is a safety relay that sits and looks at the output devices and their performance and the input devices and their performance. If there is any fault that's detected, it will then shut down the safety relay. If there is any fault on the output, it will shut down the safety relay. The difference between category 3 and category 4 is category 4 has an intolerance for missing out on faults. In simple terms, a fault that occurs will be detected, and undetected faults will still not lead to a loss of the safety function. And we achieve that in part by having much more interrogation going on between the output devices and the logic solver. And there's crosstalk between the two channels as well. At category 3, some, but not all faults will be detected, and therefore there is a slightly lower risk on your machine, and you would use category 3. But at category 4, typically something like a press application, you would definitely be looking at the higher level of integrity in your circuit design. So to summarize that, I've tried to go from left to right, and we have categories B and 1, category 2, category 3, and category 4. And we start to now introduce, well, how does that allocate itself with the performance levels? Well, very roughly, and it is a rough approximation, if you're looking at categories B and 1, you can probably select a performance level A or B. At category 2, it's B or C or maybe D. And category 3, you would be definitely looking at D, and category 4, definitely looking at E. There's a very rough approximation across the bottom. As you remember from the previous slide, we go from low to high. So, performance level. What does it actually mean? Well, as the performance level increases, the probability of dangerous failures per hour also decreases. So what we're trying to do is make it much, much, much more difficult to have an accident when you're at performance level E as a result of a component failure in your safety architecture. And the greater the performance level, the higher the integrity of the device that you put in. So we need to understand a bit about common cause failure. And there are 6 steps that we need to go through. Excuse the typing error at the top there. 6 steps that we need to go through, and we need to look at separation of components and cabling. I took this photograph a long time ago on the right-hand side. This is a result of long installation, maintenance going on, absolutely zero separation between safety function, the mains and control there. It's looking a bit of a mess. We look at it at design, we look at it when it's going in, we look at it in the field and when there are modifications. We can use and select diverse techniques. So for example, you might put a locking switch with an RFID on the door. An RFID device detects the position of the door as well as the locking switch. We need to look at the design expertise and who is in the team to do that, and who is going to actually design the safety control circuit. It's no good me going to my boss, Steve, and saying, Steve, can you design that safety circuit? You did a training last year, didn't you? And Steve's nodding. It's near pay review day, so he's saying, yes, definitely going to do that. The reality is you need to allocate people who are competent to perform the task, and they have got proven experience to do the job. We have to go through and make sure we've done proper assessment and analysis, like the risk assessments that I talked about. We have to have a training program put in place to make sure that the people who are designing it are competent, that the people who are receiving the machine are competent to maintain it. And they have proper instructions as well. And of course, the environment in which it's going to be used. It's no good putting a device into the wrong environment when you're actually guaranteeing that failure is going to occur. And you see the device on the side there. Clearly, it's an aluminium device used in an area where there is caustic. It's not fit for purpose. It shouldn't be in that plant. So the idea is you create a score. The maximum score is 65. You have to exceed 65, and the maximum you can achieve is 100. If in any area you get less than these results, that is then removed completely from the score. You can't say you're competent. The irony is, if you're incompetent, then really you shouldn't score anything anywhere. So common cause failure is a set of effects that goes into one channel and affects the other channel, but creates a common failure that leads to loss of the safety function. So the initial design going wrong and the specification and getting everything right with the safety integrity, or it could be the way that it's maintained. It could be a loss of wiring in the field. We accidentally use PVC in the field instead of armored cable, and we've got a short circuit in the field. The safety switch you see in the top corner there, that is a single safety switch. There's another one on the other side. This breaks. It's not acting properly. They're both in the same switch mode. This one fails, and we've got a common cause failure leading to the machine carrying on running on. So what do we need to do to identify a performance level? Well, within the standard, there is this rather useful graph, and initially at this stage, it'll look a bit weird, but by the time I finish, hopefully it'll look a bit less weird. We need to identify the mean time to failure to danger, whether it's low, medium, or high, for the components that make up the safety function. And then we take those components, we join them together. So we take a subsystem of each individual component, we join them together, and then we look at the MTTFD of the whole thing, whole light part of the channel. And we have to look at diagnostic coverage so that we look at the way it's being analyzed and how quickly it can detect the faults and how often it performs that check. And of course, we talk about the architectures that we looked at before. So to start that process, we need to understand about the way people are utilizing the machine, or as a machine builder, how the machine is forecast to be utilized. He can write in his manual how often and what speed it should be working at. So we need to understand the number of operations per year. And to utilize that, we understand the number of days in a year, the number of hours it's going to be utilized, and also, very importantly, the time between the start and the completion of the complete cycle, so between two consecutive component cycles. So utilization of devices and the cycle time, the average time in seconds. Tuck that away because NOP will come up very soon. We now have to have a look at understanding dangerous failure rates. I do not claim to be a mathematician, and there are lots of tools out there that can help you do this. But ultimately, we're trying to calculate the mean time to failure to danger. And I'll come on to how you get the data on that. Let's just talk about the components mathematically that make that up. We're looking at the T10D value, and that's the mean time until 10% of the components have failed dangerously. That's also known as the mission time. We're looking at the B10D value, and that is the average number of cycles before 10% of the components have a dangerous fault. We're emphasizing we're constantly looking at dangerous fault. LAND-D is the constant dangerous failure rate, which is something comes into the equation when you're looking at the mean time to failure and the mission time. And overall, the mean time to failure to danger is calculated at the bottom here by taking the B10D value, looking at your number of operations multiplied by 0.1. So in order to make the calculation, we need to look at the MTTFD for each of the elements that make up our safety system. And if you think back to those slides at the beginning with the architecture, I showed you an input, logic, and output. So for the input device on channel 1, we would calculate the MTTFD for the first device, D1, the logic solver, the logic solver device, D2, and the output device, D3. Our calculation for MTTFD is then the reciprocal of all of those devices summed together. Now, you don't have to sit and do that. You can actually go and use tools. There's one tool, independent free access tool called Systema. And Systema is a tool that everybody can enter their data on their B10D, and then they can enter in their MTTFD if it's appropriate. And that allows the customer to then make his own calculations on how to check his performance levels on his machine. Most important thing, MTTFD is defined by low, medium, or high, and the range of low is 3 to 10 years, medium is 10 to 30 years, and high is 30 to 100 years. And we do that for the entire channel. Now we get on to diagnostic coverage. So there are really two types of fault. The ones we like are on the left, the safe faults, and the ones that we don't like are on the right. So let's look at the left first of all. Safe detected faults, LANDR-SD, and safe undetected faults. Well, it's not that much of a problem for us because if it's safe and it's undetected, it's an irritation. It might affect operational efficiency, and it certainly might slow you down because you can't find out what's wrong with it, but it doesn't affect the integrity of the safety function. However, on the dangerous fault side, this is what we are trying to reduce down, and we are using diagnostic coverage to create effectively a mathematical fraction that's saying our percentage or our amount of errors that are undetected is very, very small, and therefore probability of that occurring is also quite small. But dangerous detected faults, LANDR-DD, and dangerous undetected, this is the place you do not want to be, because if you've got undetected faults and they lead to loss of safety function, you then need to add additional channels and additional monitoring and improve that if the risk is high on the machine. So diagnostic coverage is lambda DD, failure rate of dangerous detected faults divided by the failure rate of all of the dangerous faults on the machine. So where can we find that information? We can look at the manufacturer's data sheet. So when you go onto the back of our data sheet, there may be information that gives it directly for the component or the elements that make up that component. If you're designing a product yourself and it's the first time you've done it, you may, of course, have produced your own failure mode effects analysis and recorded your failure rates and done the B10D testing and such like along with that. Or if you're using a generic device like a pneumatic device or a relay, a contactor relay, motor relay, anything like that, you'll find at the back in Annex E, you can go down and select the diagnostic coverage for your particular device in Annex E of EN954. And the range that we're going from is no diagnostics right the way through to high. And the DC can sit at 60% or less than 60%, 60 to 90, 90 to 99, and then above 99%. The higher the diagnostics, the better the chances are of actually catching that fault early before it leads to a loss of safety function. And it's no surprise that later on you'll see at performance level E, we generally expect medium or high diagnostics. So we need to calculate the diagnostic coverage or the DC average. And if you remember, going back, everything is broken down into the individual elements that make up your safety channel. So for your first device, you take your diagnostic coverage that you've looked up in your data sheet, you divide it by the MTTFD that you've calculated from your number of operations per day, and then you divide all of that by the reciprocal of the MTTFD for that device. So it's device 1 plus device 2 plus device 3 up to device infinity. So let's try and build all that together now, because I've talked about categories, I've talked about architectures, I've talked about performance levels, I've talked about MTTFD, diagnostic coverage. Let's try and put that together and see where that sits, see whether or not we are in a position to say, yeah, I think I know what my performance level is going to be. So thinking back to the dual channel circuit I showed you before, there it sits at the bottom. We've done our calculations and we've identified that for the safety device and the logic solver and the relay output, we've got a high level of MTTFD. So that's tick. We then look at the diagnostic coverage and we identify from the devices in the calculation I showed you on the previous page that we're sitting between 90 and 99%, tick. We've got our architecture down here, which is shown in a dual channel architecture with cross monitoring. In actual fact, I've drawn the communications on there with a high level of mandatory monitoring between the channels. So in fact, that's category 4, but we won't argue that. And then we go back to our table and we use this table to now apply everything that we've found and have a look and see whether we've achieved the result. So we mentioned that we were looking at a high level of diagnostics. We've got medium on our DC average, sorry, a high level of MTTFD, medium on our diagnostic coverage. And you can look here, if you go to the left-hand side, you see A, B, C, D, E. And you have these bands, and wherever you sit in that band, it is possible to achieve that performance level. So you can get the same performance level using a category 2 architecture and a medium diagnostic coverage and high MTTFD. You could even do it with medium MTTFD and low diagnostics in your category with your category 3 architecture. So you use this table to choose which you're going to do. We've selected category 3 architecture with high and medium on the DC and the MTTFD. And now we can safely say that if we follow what we've designed there, we will have achieved performance level D. But that's not the end of it, because within the EN ISO 13849 Part 2, you also have to make sure that you've done a validation process. If you remember very early on, I said, make sure that you validate it, because so many people go through the process of verification, they go and do the installation, the installation doesn't actually quite work out the way it was meant to. The operations manager says he wants to go faster. You change the speed of the machine, you change the characteristics of the machine, and it's no surprise that the number of operations per day has changed, and that can influence the performance level. So you need to go back and review what you have done to make sure what you said you were going to do has actually been achieved by the safety function, and most importantly, by the process and the people that were involved in putting that safety function into service. So in the back of the 13849 Part 2, there's a validation checklist, and it's associated with the architecture. So you can go across, look at the architecture, and if you wanted to do performance level 3, so category 3 architecture, you've got a table that you can go through to make sure you've calculated everything to do with your safety function. And this goes on for 2 pages. So it's an ideal checklist. And once you've gone through that checklist, signed it off, there's one final thing you should do. You shouldn't do that checklist. A third person, third party, not outside the company, but independent of your project, but with the competency, should go through and verify that this has been achieved. Validation should not be performed by the person who designed it, because you will get a systematic error. It will sit there during the life of the machine, and it will manifest itself in that high percentage that we saw at the beginning, that 40%, 44% of errors occur as a result of design, and they remain latent in that design until something changes or goes wrong. So the method of buying and fitting components and forgetting about them the old school way, that's just completely not appropriate anymore. The failure rate statistics kind of talk for themselves, and it's a sobering reality that when we walk into a factory today, wherever we go, there will be machines that haven't yet had the accident that is going to occur, that is designed into the system, but the conditions haven't yet occurred to make that happen. So the process of calculation applies to all machines, and whether or not you make a significant upgrade on your machine. And most important thing, if you make a change on the machine, perform a risk assessment first. And then when you know what you're trying to achieve, speak to people, come and have a chat with the guys at IDEC, the safety specialists, and we'll help you solve your problem and turn it into a reality that reduces the risk that you've got in your machine that you've identified on your risk assessment. So, well, first of all, thank you for your time. I hope you've been able to follow that. I apologize for speaking at the speed of light. Just to get you know, each one of the slides there is approximately 1 hour in a training session, which lasts about 33 hours, hence the 33 slides. And we've got more webinars coming up in the future on different subjects that builds together to make that training. We're going to be looking soon about safety protection, safety protected devices, positioning of light curtains, use of laser scanners, applying them to robotics, AGVs, that type of thing. And we're also going to look about the clunk click side of safety, correctly applying safety devices in the field onto machines to make them last. And we'll be doing that alongside some colleagues and doing a Q&A session, a little bit more different, kind of mix it up a bit. So you can see that that line, that blue line goes on. Perhaps you would like to suggest a topic that you want to address. There's 2 ways we can do that. Yes, I'd be very happy to do another webinar on a subject, especially for you. But we also do things called coffee text. This is really simple. You send me an email, you make a cup of coffee, tell me when you want to talk, and you drink the coffee and I solve your problem, or my colleagues try and solve your problem. We're talking about your application and how you want to make it safe. Of course, we produce products, but we'd be more than happy to talk about what you need to do to get your machine integrity right. If you're interested in doing that, just click on eusupport@idec.com. So thank you very much for your time. Any questions? Not very quiet.
Hello, Tim. Tim, I have to say, I understand this is a very, very deep and interesting topic. So from my side, thank you for the presentation. I certainly found it very interesting. Got a couple of questions that have come through. Firstly, from Peter, do I have to update my safety circuits to meet this standard?
No, if your machine carries a CE mark, and forgive the guys in the UK SA marking is a separate little minefield, which we can talk about as well. No, you don't. If your machine was placed appropriately into market with the standards that were in place at the time, there is no need to just rush out and change your safety circuit. Just not necessary. However, if you modify the machine or you make a significant upgrade to the machine, it inherently requires a risk assessment. And at that point, you should look at the integrity of the original design and question whether or not you can do anything to improve it. Safety technology has changed and it's a constant changing. There may be better devices. There may be devices with faster reaction time. You might not have had the ability to program the safety software before, and now you have. So when you redo a machine, upgrade it or modify it in any way, you have to address the fact that the original risk assessment that the machine builder did has in fact now gone void, and you need to redo that yourself to make sure you've captured any new hazards that you've put in. I'll give you a really simple example, and I genuinely did experience this. The company removed a mechanical guard from a machine and put a light curtain in front of it. Unfortunately, it was a rotating machine tool that threw lots of bits out and it kept tripping. So by moving one type of guard over to another protective device, he in fact reduced the effectiveness of the safety function. It was a complete waste of time. So yeah, I hope that answers that question. Any other questions?
Okay. Yes, indeed. Firstly, a comment from Sylvan. Hi, Tim. Very good presentation. Great job. So thank you, Sylvan, for that. A question from, again, Peter. Do you have a database of safety-related information mentioned in this presentation, such as does IDEC have any tools to help with these calculations?
Yeah, I mean, there's two types of approach in industry. Some people like to make their own tool, so you can go to other manufacturers and they've got a tool on their website. But there's also, I touched on it in the presentation, there's a generic tool available from the German test authority, IFA. Test authority is the wrong description. They're effectively an insurance authority. And IFA produce a tool called Sistema, S-I-S-T-E-M-A. It's a fantastic bit of kit. And what you do is, as a manufacturer, we provide the IFA with our database. And then they upload that. And then as you start to build your safety system with an IDEC this and another manufacturer's that, we do live in the real world. There are lots of other devices to combine together. But as you build the system together, it allows you to put in your data of your utilization and your skills and competency and such like. And it allows you to then calculate your safety function. So Sistema is a good generic tool.
Okay, thank you. That certainly answers that one. Two similar questions here from Theo and Paul. Great presentations. Will it be possible to create a webinar with examples of correctly designed machines according to different categories? And similarly, from Tio, can you make a more tangible with short real-life reviews and samples, various machines and installations? Probably similar questions for you, Tim.
Yeah. Well, one of the things that I've just kicked off yesterday with an ex-colleague of mine is, rather than me sort of preaching at you in this, the intention is to do a kind of a Q&A session, looking at a real application, maybe use a bit of video, and then talk about the eyes and ears. So both of us are ex-safety machinery safety consultants. Well, I'm ex, he's still doing it. And what we would do is we'd look at a machine, look at it on the video, then pause it and say, right, what are we seeing? What are our eyes and ears seeing? And this is very much what we do when one of our safety specialists is able to go to site, or the customer walks around with the video. So basically he videos his machine and then we bring it back. We look at it in front of ourselves on the screen. If he's got CAD drawings, we use that and we manipulate the CAD drawings. And then we can go to the next stage, which is actually taking the safety function and doing the calculations. So yeah, it's quite a tangible thing to do. If it's a really complicated system, we'd have to break it down into slices. But yeah, quite happy to do that.
Okay, that's very good. So I think if there are particular applications, both Tio and Paul, if you would like to engage with us, with Tim, with any particular needs you have, then please do raise the questions to us. One more question, which I think you may have touched on already. Do you have more detailed trainings on these subjects?
Yes, well, it'd be lovely if I could come and see you. It'd be a full face-to-face day, or maybe a day and a half, depending on how deep we want to go with this mechanical guarding and safety-related control, or whether it's just one function. So what we decided to do is do 2-hour modular sections. You go onto EU support at idec.com, and you can just dial those up, and we can do them for you. We just do a 2-hour session. We do them sort of fairly regularly anyway. I think I've done two or three already this week, where people just want a little bit of training on a particular subject. The nice thing is when you do it one-to-one, you can start talking about what your problem is or what your concern is without divulging to the rest of the world that your machine's not quite as good as perhaps it should be. That's not supposed to be cheeky, but it's much easier to talk in detail public than in a public environment. So the one-to-one training is about 2 hours, and we do like 3 or 4 of those and build on the subject.
Okay, from my side, I think that's a very good offer to put out to all of our viewers of this webinar. So please do take us up on this opportunity to engage with Tim or one of our other safety specialists on your particular subjects.
I see, actually, there's quite a string of questions there. So what I would do after the event, I will email each of the individuals with a specific answer. There's one down here. Can you say more in future about safety functions in one machine, like an e-stop, guarding and power off? For example, can you have different performance levels in one machine, and how to approach it? Actually, do you know what? That's a really interesting subject. We could be here for another 45 minutes easily. One of the areas is that 2 machines that combine together could quite easily have different performance levels. So we have a packaging machine with performance level C, and we've got the main machine producing the tin can or whatever it is at performance level D, high speed, rotating, filling parts. So very dangerous. And yet they have to interact and work together. I take a Venn diagram approach. Sorry, I haven't got a Venn diagram to show you, but you've got performance level D and you've got performance level C. Yeah, I can definitely do many, many more examples like that, where we look at the interaction between the 2 machines, and where the performance level C machine is functioning, there's a risk that it can actually degrade that linkage between that and the D. So even though you've got performance level C, you may have to upgrade at least the output circuits of the performance level machine to a higher level of integrity, and take cross monitoring from there across to the other machine. And that becomes an absolute nightmare when you upgrade one machine, but you don't upgrade the machines upstream and downstream of it. So when you are in the industrial environment and you're doing remediation on machines, you can't just look introvert at that one machine. You need to ask yourself the question, the old school technology upstream could be a problem. So shall I modify all the safety circuit on that? And shall I do on the one before and the one before? That is a can of worms. You've got to, at some point, get to, at some point, you've got to have a cutoff, the way you say, right, the integrity of that machine won't be affected. Okay, yes, I will definitely put everybody in copy. As long as you've registered with your email address, I can certainly do that. You also will get a copy of my presentation, and you can also privately email me. Yeah, no problem at all. Great presentations. Okay, yeah. One point is somebody's asking about diagnostic functions, the difference between category 3 and category 4. On the drawings, you will see on a category 3 architecture, the interconnection means are connected. So it's a feedback contact from the output device is connected, and it's drawn dotted. And when it's drawn dotted, it means that it is only as a practical means, if it's practical. I think with modern control gear, There are very few devices where it's not practical. It is practical to actually put a feedback device in. But on category 4, it is mandatory to have a feedback device, and therefore that connection creates that feedback loop from the logic solver to the output in channel 1 and the logic solver to the output in channel 2. And then we've got 2 coprocessors sitting in the relay, cross-monitoring between the 2 relays. So yeah, I can expand on that a bit more as well. Good. Okay. Hopefully I've covered everything. Thank you very much for your time. Please get in contact or yeah, ping us for another private session. And the next one is in about 8 weeks' time. I think we're looking at safety distances and laser scanners and robotics and how to make sure your AGV doesn't run your feet over. Good. Thank you.